What's up, everybody? My name is Steve, and today we're covering USACO's 2024 Open Contest at the bronze level. Problem number 2, walking along a fence. Farmer John's N cows, where N is between 1 and 10 to the 5th. 10 to the 5th is a really big red flag. If you have 10 to the 5th and you square that, it's going to be too big. Anytime you see 10 to the 5th, that tells you are not going to be able to use an N squared solution. We're not going to be able to skip cows, which tells us that when we solve the problem for one cow, we cannot do it in linear time. We get a lot of this at silver. It's a little less common in bronze, but we're going to watch out. Anytime we see 10 to the 5th, we got to make a note of that. And we can't reduce the number of cows, so we have to make the solution faster. Farmer John's N cows each like to take a daily walk around the fence enclosing his pasture. The fence consists of P posts, where P is between 4 and 2 times 10 to the 5th. There's that 10 to the 5th again. We can't check every cow against every post. The location of each being a different 2D point, X and Y, on a map of Farmer John's fence, where X is between 0 and 1,000. And if X and Y are both between 0 and 1,000, that means the whole entire thing is 1,000 by 1,000, which means at most we have 1,000,000, and we can make an array to represent that. And that's another huge hint. You always got to watch these numbers, because that'll give you a lot of hints as far as how you're going to approach the problem. Each post is connected to the 2 adjacent posts by fences that are either vertical or horizontal line segments. So the entire fence can be considered a polygon whose sides are parallel to the x-axis or y-axis. That just means that they're going to be squared off. We're not going to have any diagonal fences or anything circular. The last post connects back to the first post, ensuring that the fence forms a closed loop that encloses the pasture. The fence polygon is well behaved in that every fence segment only potentially overlaps at their endpoints, and each post aligns with exactly 2 fence segment endpoints. So what that means is if we have segments here, they're always going to be aligned horizontally and vertically. Every post has 2 connections, and at worst, we're going to meet at the corners. Like that. But we're not going to have any where like one fence is crossing another fence and we're making weird shapes. Each cow has a preferred starting and ending position for her daily walk, each point being somewhere along the fence, possibly at posts, possibly not. That's another important thing, is the starting points aren't always going to be at posts. So we can't just record post locations. We have to record every location along the fence. Each cow walks along the fence for her daily walks, starting from her starting position and ending at her ending position. There are 2 routes the cow could take, given that the fence forms a closed loop. Since cows are somewhat lazy creatures, each cow will walk in the direction around the fence that is shorter. If there's a tie, the cow may choose either direction. So, essentially what they're saying with that is that the cow has a specific starting point and a specific ending point. And they want to get from the starting point to the ending point, but they're not particularly concerned whether they go clockwise or counterclockwise. They're willing to walk either direction, and because they're lazy, they'll go the shortest of the 2 directions. So right off the bat, what you're kind of imagining here is we've got a fence that has a variety of points. We'll demonstrate this with props in a minute. We've got fence posts that form an oddly shaped pasture, and the cow's going to have some arbitrary starting point and some arbitrary stopping point. But remember, we can't solve this in linear time. We need to figure out a way to figure out which is the shortest way to get from the starting point to the ending point in as few steps as possible without actually having to trace around the fence. Because if we trace around the fence, this is a linear problem, N. And they told us already that the number of fence posts are between 2 times 10 to the 5th, which means walking around is a linear solution per cow. And since I have 10 to the 5th cows, I've got 10 to the 5th times 10 to the 5th, which is going to be too slow. I have to figure out a way to instantly figure out how to get from here to here in the fewest steps possible. This is going to be sort of similar to a prefix sum. Prefix sums aren't exactly a bronze concept. It doesn't hurt to be familiar with it. It's not a very difficult topic, and we might talk about that again here in a minute. Input format. The first line of input contains N and P. Remember, N is the number of cows and P is the number of posts. So here I've got N and P. Each of the next P lines, here to here, contains 2 integers representing the positions of the fence posts in clockwise or counterclockwise order. Essentially, it doesn't matter if it's clockwise or counterclockwise. There's actually a problem clockwise fence. I have a video on that as well that talks about determining whether or not a fence is considered clockwise or counterclockwise. But when they tell you that it's either clockwise or counterclockwise, what they're saying is it doesn't really matter. They're just telling you we're not going to be jumping around and trying to find our own path. They're listed in the order you're intending to walk them. Each of the next N lines contains 4 integers. N lines. So I have 5 here, that's N, and then 4 fence posts. Each of the next N lines contains 4 integers, x1, y1, x2, y2, representing the starting position, x1, y1, and ending position, x2, y2, of a cow. The output format, write N integers, that's 1 for each cow, giving the distance that each cow walks. They're not asking for a series of north, north, east, north, south. They're just asking you for how far it has to go. Let's go ahead and model this problem out. I have a chessboard laid out here, and we're going to mark the fence post first. So I have a fence post at 0, 0. Instead of having it on the lines, I'm having it on the columns. It's going to make it easier to mark the fence posts. We have one at 0, 0. I'm going to have X first. So we have 2, 0 is the next one, and then 2, 2, and then 0, 2. So once again, they've given us sample input that doesn't really capture everything that this problem has to offer. But this is going to be a good way to kind of see how the problem is going to be solved out. So the first cow wants to go from 0, 0 to 0, 2. Sample output is 2. 1, 2. Next cow needs to go from 0, 2 to 1, 0. That's a little disorienting when you're used to doing row major from the top. X0, Y2, X1, Y0. They say that's going to be 3 steps, and we can see that as well. 1, 2, 3. The others are fairly similar. I have from 2, 1 to 0, 2. That's going to be 1, 2, 3. Notice if we went the other way, it would be 1, 2, 3, 4, 5. We're always reporting the shortest distance. We have 1, 0 to 1, 2. This is a tie score. It's 1, 2, 3, 4, or 1, 2, 3, 4, either way. The last one is from 1, 2 to 1, 0. Oh, it's the same thing. It's just in reverse. It's 4 either way. The field, the maximum size is 1,000 by 1,000. 1,000 by 1,000 is very important because when you're given a grid that's 1,000 by 1,000, you can just declare an array that's 1,000 by 1,000 and have a million positions, and that's all well within your memory requirements. And that's a really big hint because we need to track how many steps she takes. Now, I briefly mentioned the idea of a prefix sum earlier. I have a pretty good way to demonstrate how a prefix sum works. Let's say like Farmer John were to start here, and there's little things that he can pick up, maybe coins he can pick up on the way. So Farmer John's going to be walking along a path and picking up coins. If I'm going to be asked a series of questions, like how many are there that he's going to pick up from here to here, and then from here to here, and then from here to here, and then from here to here, and all sorts of different combinations, I don't want to have to keep running through adding them up over and over again. Because then every time I solve the problem, I have to make one pass through, which means I have a bunch of linear passes. And if I have a lot of linear passes, I'm doing a lot of repeated work. In order to simplify this, we write down all along the path how many coins he would have at any given moment. So in the beginning, he has 0 coins. After picking up the first pile, he's going to have 3 coins, 5, 9, 10, and finally 12. One single linear pass is very affordable because we're trying to avoid having to do a lot of linear passes. But look what we got. We know how many coins he has at any point on the road. If I know that as of here, he's going to have 10 coins, and as of here, he would have had 3 coins. If I do 10 minus 3, I get 7. And that means that from the 3 to the 10, he picked up 7 coins. That's 2 plus 4 plus 1, which is 7. And this will work for any 2 pairs of points, from here to here. At this point, he had 5 coins. Here, he has 12 coins. 12 minus 5 is 7, so once again, he would have picked up 7. 4 plus 1 is 5, plus 2 is 7. From here to here, he picked up 9 coins. 2 plus 4 is 6, 7, and 9. So now, instead of having to do 2 plus 4 plus 1 plus 2, we can just do 12 minus 3. From here to here, instead of going 3 plus 2 plus 4 plus 1 plus 2, we can go 12 minus 0. And this will allow us to solve in constant time how much is accumulated from point A to point B. And if you're familiar with this technique, this actually makes the fence problem a little bit more obvious. So before, we had figured out that going from here to here is 3 steps. But we know we need to do that in constant time. If I know the starting position, and I know that they're going to end at the same location, all I need to do is know how many steps they've taken along the path, the same as the prefix sum. If I know that as of here, there have been 2 steps, and as of here, there have been 5 steps, then I can do 5 minus 2, and I can get 3 steps. It doesn't get us all the way there, though, so let's try it with a little bit more of a complicated fence. So let's say like we got a fence post here, 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 and here. When we're doing our initial load, we know the order the fence posts are in. If I know I've got a fence post from here to here, I can count that out. 1, 2, 3, 4. Now I can do this very simply with a loop. 5, 6, 7, 8, 13, 14, 15, and this we can represent either as 16 or 0. It turns out the math doesn't really matter. So we're gonna have that be 16. Let's say a cow wants to go from here to here. You know that as of here, we've gone 3 steps. And as of here, you've gone 9 steps. If we do 9 minus 3, we got 6. 1, 2, 3, 4, 5, 6. Okay, that worked great. But what if we go from like here to here? If I go from 3 steps as of here and 14 steps as of here, I have to go 11 steps. 1, 2, 3, 9, 10, 11. The shorter way would have been to go the other way. 1, 2, 3, 4, 5. How do we get 5 out of 14 and 3? Well, We know that the total distance around is 16, and we know that this way around is 11, which means if you do this way plus this way, it should equal the perimeter. If you go from 3 to 14, you do 14 minus 3 is 11, 16 minus 11 is 5, which is how many steps you'd be if you went this way. Go ahead and do 1 or 2 more. Let's say like Bessie starts on the 16 and ends on the 8. As of here, I'm at 8 steps, and then as of here, I'm at 16 steps. If I go from the 8 to the 16, that's 8 steps. Or, since the perimeter is 16, if I do 16 minus 8, if I go from the 8 backwards, that's also 8. Let's go from the 9 to the 1. We'll always calculate initially from the smaller number. 9 minus 1 is 8, and since the perimeter is 16, if we go the other way, 1, 2, 3, 4, 5, 6, 7, that's also 8 steps. Do an offset one. From 13 to 1, if I do 13 minus 1, that's 12. And if I have 16 minus 12, I've got 4. 1, 2, 3, 4. A moment to clean these off. The way the coding algorithm is going to work, you load your first fence post, you load your second fence post. You figure out, how do I get from here to here? Any kind of a loop would be good for this. In this case, this is from 1, 1 to 5, 1. X is in the increasing direction, and then Y has to be the same. So I have to have some sort of a loop that'll count from here to here. And I need a counter that'll keep track of how many steps I've taken. So when I go from here to here, that's 1, 2, 3, and the fence post is 4. This is just a 2D array. You can imagine it upside down if you think about it in terms of rows and columns. It actually really doesn't matter. If you haven't worked with 2D arrays a lot, you can treat either one as X and Y. You can treat either one as a row or column. As long as you're consistent, you can solve any kind of problem. If I initially declare it as 1,000 by 1,000 and I want the first one to be X, it doesn't necessarily have to be 0 to 1,000. It could be 0 to 1,000, or it could be 0 to 1,000. It really is just however you imagine it, so you don't have to worry about that. As long as it's 1,000 by 1,000, also then it's square. So as long as you're consistent about which one is X and which one is Y, it'll work out fine. So I've got 5, 1 to 5, 3. The X's are the same. The Y goes from 1 to 3. So we have to have our loop increasing the Y. 5, 6. Going backwards from 5, 3 to 3, 3, I need to realize that my Y is staying the same, but my X is going down from 5 to 3. So I need to set my loop up, count backwards. And all I have here is a big 2D array of integers, and I'm just filling in integers. I would recommend using while loops for this. I like to have things in terms of x1, y1, x2, y2. I would also have a secondary variable called dx and dy. dx just means delta x and dy means delta y. In the case where you're going up in terms of y, you would set your dy to 1 and your dx to 0, and then you just keep adding dx to your x and adding dy to your y. That'll be adding zeros to the x position, adding ones to the y position will work its way up. When you're going backwards in terms of x from right to left, you can make your dx be -1 and your dy be 0. If my dx is -1, then every time I add -1 to my x position, it'll go down by 1. If my dy is 0, adding 0 doesn't change it. And we'll get to that in the coding section in a minute. That's how I would visualize this. And again, the big hints here that the board is 1,000 by 1,000, which you can do with an array. And also the fact that there are 10 to the 5th cows, which we have no way to reduce that. So we have to do 10 to the 5th solutions. And because the number of fence posts is also 10 to the 5th, we can't go fence post to fence post for each cow from their starting fence post to their ending fence post. If you wrote code like that, you can get through, I think, about the first 3 or 4 test cases, but it'll time out on the end. The key to this is that we can afford to have a 1,000 by 1,000 array. And any areas where there's no fence post, where Farmer John didn't pass through, we'll never look at those anyway. 1,000,000 steps is also well within your time complexity. And it's good to be familiar with time complexity. 1,000,000 is 10 to the 6th. 10 to the 6th is tiny. 10 to the 6th will run in a split second. We'll see that also in a minute when we write the code. That's it for the explanation and for the visualization, and I'll see you on the coding section. All right, so to start with, we're just going to set up a basic sanity check just to get things going. I'm going to go ahead and paste the input file ahead of time. So my first number is n, which is how many cows there are. The cows are down here at the bottom. My next number is p, which is how many fence posts there are. Those are right here. So what I'm going to do is I'm going to make a 2D array that's 1,000 by 1,000. I'm going to make a function that will go from a starting fence post to an ending fence post, so from 0, 0 to 0, 2, and it'll walk along and fill in numbers. I could build a class if I wanted to make this proper design, or I could pass by reference, but just for the sake of the speed of writing as well as keeping things really easy, I'm just going to make a 1,000 by 1,000 global array to represent the different squares on the farm, as well as a global integer for the number of steps taken. So we're going to do int steps equals 0, int field 1,000 by 1,000, void walk to, int start x, int start y, int end x, int end y. And that's going to do whatever work it needs to do to go from this starting location to this ending location filling in steps along the way and adding 1 to the number of steps every time. Int np, cn np, and then I have a loop, I listen pi++ to bring in all the fence posts. This first fence post is going to be the final fence post as well as the first. I could load this into a vector of pairs and process it. I don't want to store it if I don't have to. And I don't need to store this because the whole point is to run through these and generate numbers. And after it's done, I don't need to look at it again. So rather than storing it into a vector of pairs or into a 2D array or something, what I'm going to do instead is I'm going to process it as I go. In order to walk from a starting point to an ending point, I need to have the starting point, the previous location where the last fence post was, as well as where the next fence post is. So to start off with, I'm going to have int first x, first y. I'm going to cn first x, first y. And that'll represent the starting point, which will be 0, 0. And I'm gonna then connect at the end to first x, first y. That'll be the ending location. But in the middle part here, I want to load these posts one by one, starting with 2, 0. I wanna load 2, 0, and then go from the previous fence post, which was 0, 0, to 2, 0. And then load the next one. Go from the previous, which is 2, 0 to 2, 2. Load the next one, go from the previous 2, 2 to 0, 2. And then finally go from the previous of 0, 2 to first x, first y. Int previous x, previous y. I'm gonna set previous x to first x. What that's gonna do is in my loop, I now have p-1 posts to load. So I'm gonna start I at 1 because I've already loaded the first post. And for every post I load, we're gonna do int next x, next y, cn next x, next y. We're going to walk to, and we're going to walk from the previous x, previous y, to the next x, next y. And then I'm going to record next x as my previous x. I'm going to set my previous y to my next y. That way, the one that I just loaded will become the previous one for the next loop around. And then finally, I'm going to do walk to from previous x, previous y, to first x, first y. Just to make sure we have all that logic in order, I'm going to print out what's happening in walk to. Walking from start x, start y, to end x and y. 80 column limit. Let's go ahead and compile that and just see where we are. I'm going to do make walk-in. Make is going to be fine for this. We don't need to do anything fancy. /walk-in, and then copy all this. Actually, I'm going to stop before the cow inputs because we haven't even handled those yet. For input. Here we go. All right. So walk from 0, 0 to 2, 0, 2, 0 to 2, 2, 2, 2 to 0, 2, and then finally 0, 2 to 0, 0. In order for this to work now, rather than printing this, I need to actually go through the process of filling in those numbers in that 2D array. So the way I want to do this is I'm going to have a dx and a dy. The dx is basically your rate of change, your delta x per time step. Every time one step occurs, what is x changing by? What is y changing by? Those are all either going to be 0 or 1. So we're going to do int dx dy. Start both of them as 0, might as well. dy equals 0. Also, I could stack these. A lot of people do this kind of thing. I don't care for that, so I'm just going to keep it expanded out. I think it's a little easier to read. So I have dx and dy. I'm going to set dx and dy both to 0. And then if start x is less than end x, then dx has to be 1 so that I can go from the starting point plus 1 to the ending point. Else, if start x is greater than end x, I gotta go the other way. dx equals -1. And if they're equal, then my x won't change at all. Same thing for y. If start y is less than end y, dy equals 1. Else, if start y is greater than end y, then I have to go dy equals -1. I'm going to add 1 to the number of steps. I'm going to record the number of steps in my field, and I'm just going to keep doing that until I get from my starting point to my ending point. I don't have any sort of safety checks in here. If they're misaligned, for example, if I got a diagonal and I got a dx and a dy of 1, and it goes diagonal and it misses, it's just going to be an infinite loop till it crashes. None of the test cases are going to do that though, so we're not going to worry about trying to filter stuff like that. Also, just to kind of compress this a little bit, you don't need curly brackets, and white space is always optional, which means I don't even really need to put this on the next line. I'm going to put these all on single lines. I don't usually do stuff like that, but I feel like in this particular case, it's going to be a little easier to read. Also, this function is going to get a little bit long, and I want to be able to keep the whole function on the page at a time, just for the sake of the recording. So if start x is less than end x, then dx is 1. If start x is greater than x, dx equals -1, and so on and so forth for y. And actually, just since we're on the topic, you could put curly brackets on this. I could do that. I feel like that's too cluttered, though. While start x is not equal to end x, and start y is not equal to end y, then what I'm going to do is add 1 to my number of steps. I'm going to set the field field at start x. I guess this should be current x, current y, if we want to make that more accurate, because that's where you currently are. You're getting from the current position to the ending position. Let's go ahead and rename that. Sometimes when I'm writing code, I'll name variables badly, and then I'll get myself confused halfway through and then end up making mistakes later because the variables aren't doing what I thought they did. So while my current x is not my ending x and my current y is not my ending y, then field at current x, current y is equal to steps, current x plus dx, current y plus dy. No, actually, I gotta move first and then write. So wherever my current position is should already have a number written to it. I'm gonna add to the number of steps, move to the new location, and then write the number of steps in that location. That's gonna go all the way around until it hits the final ending point, and then the ending point is where it's gonna write the perimeter. We also will have steps at the very end to know what the total perimeter is. And steps will be exactly what the perimeter is. Let's run that real quick and see if we're getting the right values. Cout perimeter is gonna be steps, be the total number of steps taken. We'll just make a real simple for loop for I equals 0, I is less than 3, I plus plus, j equals 0, j less than 3, j plus plus, cout field ij, cout end line. We'll make that, oops, oh, spelled that wrong. Where is that? It should be current. Current y. Try that again. The field didn't record the values and the perimeter didn't happen either. This needs to be an or. It's not while they both are not equal, because the y, either the y will be equal or the x will be equal. It's while either one is not equal. As long as either one is not equal, we haven't solved it yet. Let me rerun that. Okay, there we go. So I got a perimeter of 8, and then here are the numbers. We started at 0, 0, which is actually the top left because I'm printing it row major. And again, the XY row major thing is really confusing. A lot of times I'll just convert to rows and columns, and it doesn't really make a big difference. So from here, I took my first step and wrote a 1, because I'm going from 0, 0 to 2, 0. Whichever dimension can be x or y or row or column. It could be bottom to top or top to bottom or left to right, right to left. As long as you keep it consistent, it's fine. So when I go from 0, 0 to 0, 2, even though that was x0, we're kind of imagining x is going vertically down and then y is going up, just because that makes it easy. And then you can kind of imagine the whole graph tilted sideways. So 0, 0 to x of 2. So we're going to go x of 1, x of 2, and this will be x of 2, y of 0. And then from 2, 0 to 2, 2, we go y plus 1, and then y plus 2. We'll go back to x of 0, which is where that 6 is, and then back down to 0, 0. And you just kind of, again, can imagine it tilted sideways, because that just makes it easier to print. Step 1, step 2, 3, 4, 5, 6, 7, and 8. I've got a perimeter of 8. And now what I'm going to do is I'm going to run my queries, which will give me, from this arbitrary place to this arbitrary place. And again, as long as I'm consistent about making x be the first dimension of the field and y be the second dimension, and when I do my walking around, it'll all be relative anyway. Let's go ahead and write those. For int I equals 0, while I is less than n, I plus plus. So we have starting and ending again, previous and next. Here I've got previous and next already in use. Now I'm going to do start and end. I have current and end up here, but that's a different scope, so that won't be a problem. Int start x, start y, and x and y, cn start x, start y, and x and y. I'll need to figure out the distance from the starting to the ending point. Now, the way that they walked this, it's possible that they're going to walk all the way around. They might start, for example, at step 7 and walk to step 1. Or they might start at step 5 and walk to step 7. When I do this, I may end up with a negative number, depending on how the math works out. I can always correct that to positive just by adding the perimeter, but we're gonna have to kind of fiddle with that and see how that works. And I always wanna get the smallest of the two directions. Int steps taken is going to be field at start x, start y, minus field at end x, end y, which might be negative. If steps is less than 0, then I'm just going to do steps equals negative steps. It's just going to be easier to work with. And then finally, the number of steps. This is like clockwise, I suppose. CW steps. Let's rename that. CW steps. CW steps. And then I'm going to do int CCW steps is going to be perimeter minus CW steps. That's how many counterclockwise steps there are. Since CW steps is always going to be positive, that'll always give me the positive equivalent. So we're going to do cout CW steps for CCW steps. All right, let's remake that. Perimeter. Oh, steps is the perimeter. Let's remake that. Grab my full sample case now. We'll paste that in and just see if the choices make sense. Oops, what happened? Oh, I didn't run it. Snort. Walk-in. Have to run the program for the program to run. A rookie mistake. So, okay, so let's have a look here. And this is actually kind of what I was looking at. So we walk around this little donut, and I've got my little donut right here. And the first walk is from 0, 0 to 0, 2. 0, 0 is where the 8 is, 0, 2 is where the 2 is, which is going to be either 2 or 6. And that makes sense, because if they go positively along X, it's 1, 2 steps. If they go the other way, it's 1, 2, 3, 4, 5, 6. So 2 or 6. Which one's smaller? Let me look at my expected output real quick. Here are my expected outputs. Let's paste those in here. Now, if I've done this correctly, then whatever the smaller number is for each of these should be the expected output. So 2 or 6 is going to be 2. 5 or 3 is going to be 3. 3 or 5 is going to be 5. 4, 4, 4, 4. It looks like we're already done. Let me comment out the output statements that I was using for debugging. Let's comment out perimeter. And then for this OR, basically, if CW steps is less than CCW steps, then I'm going to see out CW steps, else see out CCW steps. And this will also handle if they're equal to each other. It's just going to be an else. So if they're equal, then it'll just be CCW steps, and it'll be equal, so it won't matter. I also need to comment out this blob right here. Output's my field. Let's compile. Make walk-in. Just going to pretend none of that ever happened. Walk in, throw in my sample input, paste, 2, 3, 4, 4. All right, let's submit it and see what happens. Plus, choose file, walk in, open, submit. Ooh, missed the 11th test case. What have they done here? All right, so I've overlooked an edge case. Oh, I made a rookie error. I made my field 1,000 size, which is actually 0 to 999. Upon rereading the problem, I see that the fence posts are between 0 to 1,000, including 0 and 1,000, which is actually up to 1,001. I need to have index 1,001 available to have an X and a Y of 1,000. So I think the reason I'm failing this last test case is probably related to that. It's interesting, though, that they didn't have any fence posts at the 1,000 marker until the last test case. I'm almost sure that that's going to be what that is. Let's just resubmit it directly. C++. The people doing C++ get the benefit of watching me make the rookie errors. And then when I move on to the, oops, I got to take all that output out. And then when I move on to the Java, I'll look a lot smarter when I do the Java because I won't make those same mistakes. Let's try that again. Oops. And as expected. Okay, so 2 things. One, it was really generous of them to not have any fence posts at the 1,000X or 1,000Y into that last test case, because if you overlooked that, which I did, you only would have missed 1 test case. 1 out of 10 is going to give you 300 points on this out of 333, and that's not bad at all if your goal is just to pass, especially at bronze. We don't care too much about the score at bronze. We just want to move on to the next level and try to understand the problems. Okay. Onto the Java. We're going to import Java util scanner, class walk-in, public static void main, string args. In case you skipped the C++, I'm going to be making static int variables. Steps is going to start at 0, and static int field equals new int 1001 by 1001. I made this mistake on the C++. We have to do 1001 because the fence posts will be from 0 up to 1,000, which means index 0 needs to work and also index 1000 needs to work. For index 1000 to work, the field needs to be 1001 by 1001. Int n p n equals sc. Oh, we got to create the scanner. Scanner sc equals new scanner system n equals sc next int. P equals sc next int. We're going to load the first fence post. Start x, start y, start x equals sc next int, start y equals sc next int. We're then going to record that into our previous location, previous x, previous y, previous x equals start x, previous y equals start y. So I want to try and do this all in a single pass. So what I'm going to do is as I load fence posts, I'm going to go from my previous fence post to that fence post. I'm going to walk there. I'm going to use a method for that. Public static void walk to int current x current y, int end x, int end y. Essentially what my goal is to get from the current location to the ending location, marking my steps along the way. As I'm going through loading fence post, what I'll do is I have my starting fence post, which is my starting x. I'm going to record that as my previous location. For each additional fence post, I equals 1 actually, because we've already loaded the first fence post. For all the remaining fence posts, I less than p I plus plus. We're going to do int next x, next y, next x, sc next int, next y, sc next int. And then we're going to call that walk2 function. Walk2, previous x, previous y, next x, next y. And that'll get us from our previous location to our next location. Previous x, previous y, next y. I'm going to record the next location as my previous location, and I'm going to loop back around. Then finally, when I'm done, I'm going to do my last walk2 from my previous x, previous y, to my starting x, starting y. And then that'll get me back to my starting point. Let's go ahead and just do a real quick sanity check. System out println, current x, current y, to end x, and y, Java C, walkin.java, Java walkin. Let me grab my sample input. And we have just this first part because I haven't gotten to loading the cows yet. Paste. 00 to 20, 20 to 22, 22 to 02, and finally 02 back to 00, my starting point. It looks like it's gone full circle. One other thing to point out, there's nothing that says that the first value has to be vertical and the second value has to be horizontal when we're dealing with a 2D array. If I want, I can make this first one be x and the next one be y. Now, when I actually go through and print them out, it's gonna print rotated. For int I equals 0, I less than 3, I plus plus. For int j equals 0, j less than 3, j plus plus. System out print field ij plus a space. System out println. We're going to recompile, rerun it. I think it's still on my clipboard. Yeah, there we go. Ooh, it didn't write. Oh, I need this walk2 method to actually go through and fill in steps. In order for that to work, I want to try and figure out which direction I'm going. I'm going to have an int dx and dy. dx is just delta x. It's every time I take a step, how is my x changing? dx and dy are both going to start at 0. dy equals 0. If current x is less than ending x, then my current position is less than my ending position, which means I need to add 1. I need to be going to the right. So we're going to do dx equals 1. Else, if current x is greater than ending x, then my dx has to be negative 1. And then my else is just 0, because then if they're equal, then I don't need to go left or right. I'm just going to keep my x the same. In order to kind of clean this up, because this is going to be kind of a lot of code and I want to keep it all on the page, I'm going to get rid of my curly brackets. And I did this in the C++ too. You don't have to do this. I usually don't like to do this, but the reason I'm doing this is since it's only one line, sometimes I like to put them on the same line just to compress the code, because otherwise it's kind of a lot of if statements. You could also use a ternary expression. I could do something like dx equals current x less than end x question mark, then 1, else current x greater than end x and negative 1, else 0 something. Anyway, we're just going to keep it simple. I'm not going to do anything fancy. I'm just going to have an if-else if current y less than end y, then dy equals 1, else if current y greater than end y, dy equals negative 1. And I'm not going to put any sort of safety checks in place here. If it runs out of bounds, it runs out of bounds. I'm not going to worry about it. The test cases they provide are all going to be well behaved. So if I have like something diagonal where they're going to end up missing each other, or if it's misaligned slightly and then it's going to run over, we're not going to worry about that. We're not going to worry about fence posts being out of bounds. We're just going to trust that all the input is correct. We just want to be as fast as possible, and we don't expect there to be errors in the input file, so we won't check for them. And then while my current x is not equal to my ending x, or my current y is not equal to my ending y, one of the two is different. While they're different, then what I want to do is I want to take a step, steps plus plus. I want to record that in the field, but I need to move before I record. Current x plus dx, current y plus dy, and then field at current x, current y equals steps. I think that's all there is to it. Okay, let me recompile that. Java C, I'm going to run it. Paste. So then you can see my field here. And again, this is the 0, 0 starting location. I took my first step and marked a 1 that was heading in the x direction as I'm going from 0, 0 to 2, 0. This is x2. And then I headed up. So it brought me 3, 4. And then I went left, 5, 6. You gotta kind of turn your head sideways. And then I went down, 7, 8. I ended there. That looks great. I'm gonna get rid of my output here. I'm gonna get rid of these lines here. And now let's load the cows. for int I equals 0, I less than n, I plus plus. And then each cow is represented by a starting and ending point. Start x, start y, and x and y. Note, I did use end x, end y up here in this function. That's in a different scope though, so I don't have to worry about any issues with the variable names being the same. It's important to be familiar with how scope works. In this case, because they're separate functions, I can reuse the variable and it's not a problem. Start x equals sc, next int. Start y. This is one of the things that I prefer C++ on is when you have a long sequence of integer inputs. C++ handles this, I think, a lot cleaner. And x equals sc, next int, and y equals sc, next int. And then finally, I want to get the two values. I'm going to get the label on each of the starting and the ending location. System, println, perimeter, steps. So the number of steps, the 8 that I wrote here, I'm just doing this to just make sure that I didn't, add 1 on accident. A lot of times things are off by 1. Off by 1 errors are really common. So I add the number of steps, I move, I record it in the field. The last time I did that, it was 8. 8 is in fact the perimeter, 1, 2, 3, 4, 5, 6, 7, 8. And I'm going to need that for the calculator. So I'm going to print this out here just to make sure I didn't get 9 or something goofy. We're going to have our clockwise steps is going to be field at start x, start y, minus field and x and y. Counterclockwise steps is going to be my perimeter, which is steps, minus CW steps. I'm going to print them both out just so I can compare the two. Print line, CW steps, CW steps. Oop. Oh, I did already use that. All right, I'm going to call this from x. That one's not in a different scope. From y. Let's see. Catch it. That's it. Let's grab the whole input this time. There we go. Okay. So, here's another important note. Sometimes these are negative because it'll give us a starting and ending point. So if I go from 7 to 1, I would have 7 minus 1, which would be 6. But if I go from 5 to 7, I'd have 5 minus 7, which is negative 2. So I just have to correct for that. That's really easy to do. Basically, after getting my clockwise steps, if CW steps is less than 0, CW steps equals negative CW steps. Was I copy pasting? No, I wasn't. We're good. And then these options down here are the clockwise steps followed by the counterclockwise steps. Whichever is the smallest of any of those two would be the answer. And that should line up with our answers here. So I got 2 between 2 and 6. 2 is the smallest. Between 5 and 3, 3 is the smallest. Between 3 and 5, 3 is the smallest again. And then 4, 4. If CW steps is less than CCW steps, system out print line CW steps else, and then if they're equal to or greater than, system out print line CCW steps. Comment out the perimeter. Let's go ahead and throw that in the website and just see what happens. Java, walk in Java, submit. There it goes. Grading server is busy tonight, apparently. Just to point this out, I goofed on the C++. When I initially made the array, I forgot to make that 1001. I made it 1000. And it didn't give me any errors. It just ran. Because one of the things that's different between C++ and Java is if you go out of bounds on an array, most of the time C++ will just let you do it. It just gave me back crazy numbers. If I were to have done that on Java, let's see what the difference is. The different languages you choose can give you different problems because there are certain situations where Java, in the Java version, I got errors. The code crashed. In the C++, it didn't. It just gave me incorrect answers. So it was a lot harder to debug because if I know that it's crashing, it's like, oh, okay, well, why is it crashing starting from 7? From 7, there's no additional constraints. The initial constraints are x and y are between 0 and 100 and n is less than 100. And then I think about x being 0 to 100, but then it's 0 to 1000. I realize, oh, 1000 is going to be too small. I need to make that 1001. That's really clear in the Java. I prefer C++ in terms of both the speed that it runs as well as the speed that you type it. However, if you make a mistake like this in C++, I'm not going to see errors. It's going to run, but it'll just give me wacky responses. Now, in this case, 7, 8, 9, and 10 worked by coincidence, but 11 didn't, and it didn't crash. It just gave me the wrong answer. That gives me a lot less to work with as far as what's going wrong. So this is one area where Java actually is very nice because it will tell you that you've gone out of bounds, and C++ won't tell you. All right, on to the Python. Let me grab my sample data right off the bat. First thing we do is read n and p equals map int onto input dot strip dot split. We have our initial post, start x, start y equals map int input. I should just copy this. This is going to happen a bunch. So I need my starting position, which is going to become my previous position. Previous x, previous y is going to be starting x, starting y. And in every case, I'm going to go from my previous position to my next position. And the starting position is my initial previous position because I've already loaded that. After that, I'm going to load each sequential fence post, and I'm going to go from the previous location to that next location. In order for that to happen, I need a function. So we're going to make a nice function here. Def walk2 current x, current y, and x and y. So I'm just put print from cur x, cur y to and x and y. We'll use this to test my reader as I'm going. And then for I in range 1 to p, because the first fence post has already been loaded, next x, next y equals, oops, I copied the equal sign already, equals that. And we're going to do walk2 previous x, previous y to next x, next y. We're going to copy into previous x, previous y, the values of next x, next y. By the way, this is really easy to do in Python, copying two values into two values. You could also just do previous x equals next x and previous y equals next y. This is pretty clean though. It's pretty easy to read. And then finally, when I'm done, after going through all my fence posts, I'll walk to from the previous x, previous y to my starting x, starting y. So I get back into my starting location. For this to work, I'm going to need a grid. So we're going to go ahead and create one. But for right now, I'm just going to run it. Let's clear Python 3 walk-in pi. And then I'm going to grab my first part of my input here and paste. Just make sure we're on the right page. So, okay, 0, 0 to 2, 0, 2, 0 to 2, 2, 2, 2 to 0, 2. And then finally from 0, 2 to 0, 0 brings me back to my starting location. For this to work, I need to have a grid. I'm going to make my grid be an empty list. And then for I in range 1001, I need 1001 because I need to have 0 and 1000 as potential fence post indexes. For I in range 1001, I want grid to append a 0 times 1001. They're never going to have us walk from a location that there is no fence to a location there is no fence. So we're not going to error check. Same thing later with walk2. I'm not going to do any kind of check to make sure that either current x or current y are aligned with the ending point. I'm just going to trust that the data is all good and we'll just run with it. I need a dx and a dy to be both equal to 0. If current x is less than my ending x, then that means that I'm currently to the left of where I want to be. I'm going to set my dx equal to 1. Dx equals 1 just means how my delta x, it's how my x is changing. If dx is 1, then every step my x is going to change by 1. If current x is greater than ending x, then my dx is going to be negative 1. And then I don't need to make an else because my else is just going to be that it's 0. Because if the starting and ending x is the same, then it's just x to x. Likewise with my y, if current y is less than ending y, dy equals 1. If current y is greater than ending y, dy equals negative 1. And then what I'm going to do is while current x is not equal to ending x, or current y is not equal to ending y. As long as either one of the two are different, then what I'm going to do is take a step forward. Steps plus 1. Oh, I need to have a steps variable. Steps equals 0. I'm also going to need to global those in. Global grid steps. We don't usually like to use global variables in real programming, but for algorithm stuff, we're allowed to do whatever we want. If we wanted to be really clean about it, we'd build a class, and then we could feed the queries to a class, and the class would have self variables. This is fine though for competitive coding. You want to try and keep the code short, easy to type, and simple, and using global variables accomplishes all those. Steps plus equals 1. We'll do current x plus equals dx, current y plus equals dy. I called it grid this time. Let's call it field. I called it field everywhere else. Field. It is a grid, but more specifically, it's a grid representing a field. I don't like to call my arrays array or my lists list. One, because if you call list, that messes up the list constructor. And then also just because then later when I'm reading it, I don't know what it is a list of. So field, current x, current y is equal to the number of steps. And that should be all there is to it. Let's go ahead and test that out. In range 3, for j in range 3, print field ij. And there's going to be a space. If you're not familiar with the end space, that means that at the end, after printing this, instead of going to the next line by default, I'm just going to put a space instead. Copy fresh data, paste. Because everything's relative, it actually doesn't matter if I use this as x and this is y, or if I flip them, or I try to make 0 the bottom or 0 the top. In this case, this looks a little weird because as my first fence post goes from 0, 0 to an x of 2, it should be moving to the right. But if you look at it, you have to turn your head sideways because it's actually moving down. This is x1, this is x2, and then this, as it goes up, is y1, y2, then it goes to the left, and then it goes down. And if you have your head tilted sideways, it all fits. And again, because it's all relative, as long as I stay consistent with then loading my cows and using my x as my first value in my list and my y as my second value, the fact that it prints sideways is just a matter of because of how I printed it. There's nothing that inherently means the first thing has to be up and down and the second thing has to be left and right. So you can change the X, Y to row column. This is a major confusion though that comes up in a lot of problems. Again, I always just make X be the first value, Y be the second value, and then I just treat it like it's row column instead of X, Y. So then the next thing to do is we're gonna do for I in range N for all my cows. I have 4 values I need to load. We're gonna have from X, from Y, to X, to Y. It's gonna be map and S. This is where the cow is walking from and to. In order to know how far they walked, I'm gonna have my clockwise distance is gonna be my field from X, from Y, minus field to X, to Y. Depending on how the data is given to us. If I'm going from 1 to 7, and I do 7 minus 1, I get 6. But if I'm going from 7 to 1, I'll do 1 minus 7 and get negative 6. I want to make sure that I cancel out all the negatives though. If CW distance is less than 0, then CW distance will equals negative CW distance. And then finally, my counterclockwise distance is going to be my number of steps minus my clockwise distance. So steps will be at 8. 8 is the perimeter. So if I do the total number of steps minus the clockwise distance, it'll give me the distance going in the other direction. For right now, I'm just going to print them both. CW dist, CCW dist. I'm going to comment out the grid as well. I don't need this anymore. Because of this is a scripting language, in Java and C++, they remove comments when they compile, and the compiling time doesn't count against your runtime. In Python, because it's a scripted language, it does need to read through the comments, so it'll hit that hashtag, and then it still, I think, has to scan the line. So technically deleting the comments does save you a little bit of time. It's really negligible though. We're gonna run walk-in. I'm gonna feed out in the full test data. So you can see my output here. I'm printing out the clockwise distance and the counterclockwise distance. In every case, it's a pair. Whatever the smaller of those two is what my output should be. So the first one should be 2, 2, 6. Next one is 5, 3. 3 is the smaller of the two. Next one is 3, 5. 3 is still the smaller of the two. And then 4 and 4. I don't like to use the min function for whatever reason. I'm going to just do if CW distance less than CCW distance, print CW distance, else print distance. And just as a real quick recap, if you haven't seen this before, essentially what I'm doing is I'm getting the input, I'm stripping off the new line, I'm splitting it into a list, and then I'm mapping, which means I'm applying this function. I'm going to apply the int function to all the values. When I have 5, 4, it reads in it as a string 5, 4, a new line. When I strip this, it takes off the new line. When I split it, it turns it into a list of 5, 4, and then when I map int onto it, it applies int to the 5, which produces 5, and applies int to the 4, which produces 4. And then when I do something like x, y equals that, it unpacks these, so x gets set to the first one, and y gets set to the second one. And it's just a really short way to grab all those values and stick them into 2 variables. Let's just go ahead and throw that into the submission thing, because I think we're good there. 3, choose, walk in py, submit. Almost done here. All right, beautiful. All right, just one other thing to point out. In C++, when you go out of range on an array, it doesn't necessarily throw an error. And I had an issue with the C++ in case you skipped straight to the Python. I'll just show you what happened here. I did 1,000 by 1,000. If you submit that as a C++, this is a little bit of a disadvantage to C++, is there's a lot of things where it would be an error in Java or Python, but it's not an error in C++. If I keep this too small, then anytime there's a fence post that's 1,000, it just gives me corrupted data. It doesn't give me a hard time about that though. It just rolls straight through. So what happens in C++ when you do that is your last test case fails, but it just gets the wrong answer. It doesn't crash. It doesn't really give you a clear reason why that happened. If I were to do the same thing in Python, it's going to give me a real big heads up as to what went wrong. 3, choose, walk in py, open, submit. Notice as soon as I hit test case 7, exclamation means it crashed. And then I go down here and I look at the scoring constraints and it says 2 to 6, x is between 0 and 100, inclusive, and n is less than 100. If my code is crashing, that tells me that something has gone out of bounds most likely. And then I go back and I reread the problem and I say, oh, x is from 0 to 1,000, which means 1,000 needs to be included. This is a lot easier to figure out what's happening and fix than in C++. So despite the fact that I do really like C and C++ a lot, and they are very fast, sometimes you don't get as much information back out. Also, a lot of times when I'm doing these, if I have time, I'll write one in Python first and then convert it to C++, or write one in C++ first and convert it to Python. Or I'll develop both at the same time, because sometimes that can give you just a little bit more information. If you're at a dead stop trying to write code in Python and you are familiar with C++, or vice versa, sometimes you take a stab at it in the other language and it'll be easier. And I've had contests where I'll do one problem in C++ and then one problem in Python, because sometimes I just feel like one tool is better suited for a problem than another, especially when there's permutations involved. Python is really smart about doing permutations. So let me go ahead and just fix it real quick so that I can sign off with all green. That way, if I look at it later, I'll feel proud of myself. But otherwise, yeah, that's it. That's the Python version. I don't have any funny gags or jokes for this one, honestly. It's a pretty straightforward problem, pretty straightforward representation. I really did enjoy playing with the chessboard, though. Hopefully that was helpful for you visualizing the problem, and I will see you on the next one.